Introduction to Causal Inference from a Machine Learning Perspective. So you can go through this book later on, but we will be talking about these slides, the course. So causal inference is basically inferring the effects of any treatment or policy or intervention. For example, we discussed that uh, in medical science, you would like to study what is the causal effect of medicine or an intervention, right? So, for example, the effect of treatment on a disease, effect of climate change policy on emissions, effect of social media on mental health, and you can think of anything, effect of X on Y. So we talked about correlation, why it is not, it might not imply causation. So, okay. So first we'll see this Simpson's paradox for COVID. So there is new disease COVID-27 and you have a treatment. So you have treatment T, which is A0 and B1. Okay, so this is U. And so the condition so can be classified into two types. That the condition of the disease, that either it is mild or severe, and the outcome is that uh, you are alive or you are dead. So treatment can be 0 or 1, condition can be classified as 0 or 1, and the outcome also can be classified as 0 or 1. Now this is the mortality rate table. So A is the all the people who have been given the treatment, and B comprise of the people who have not been given the treatment, or B is the people who have been given the treatment. So the mortality rate in case of A, so 240 people are died out of 1500, and in case of B, that is when the treatment is given, 105 people died out of 550. So 19% are dying here, 16% mortality rate in this case. And then you can also classify as it into mild, severe, and total. So when you classify it as mild, severe, and total, so we can see that in case of the treatment, when the treatment is provided, so you can see that there is a reduction in the mortality rate. However, in the overall sense, that the mortality rate for B is when you provide the treatment is higher. Okay, so how are they computing this mortality rate? So these are the computations. And so which treatment should you choose? Whether you should choose treatment A or you should choose treatment B. And this is the causal graph. So C is the condition. You can just say, okay, so the treatment is a causal child of the condition. So you will get the treatment based upon your condition, and based upon the treatment will be the outcome, whether the person died or he or she is alive. And the condition can also directly affect the outcome. For example, if the treatment is not given, then the condition, whether it is mild or severe, can decide whether the person died or the person is alive. So in, yeah, we can see that. So if this condition is mild, then you give and you give this treatment A, and if in scenario 1 the condition is severe, so you give the treatment B. Okay, so yeah, so then you can see that your causal graph can also change based on the scenario. Okay, so the treatment can decide the condition, which in turn decides the outcome, and treatment also can directly decide the outcome. So, okay, correlation does not imply causation. Sleeping with shoes on is strongly correlated with waking up with a headache. But does sleeping with shoes on lead to a headache? I mean, that that might not be the cause. Drinking the night before might be the actual cause. So you're drinking the whole night and then you slept with shoes on, and drinking the whole night you are getting up with a headache. So these two might be correlated with each other, but they are not at all causally linked with each other. So shoe sleepers differ from non-shoe sleepers in a key way. And here is the concept of, we discussed about the confounding. So what is the confounder here? So that you slept with the shoes on, and you are thinking that, okay, that is a causal parent of headache. So that is actually a confounder, like that's causing confusion in the interpretation of the analysis. So this is the confounding association. Okay. And so correlation is a mixture of causal and confounding association. And okay, so this is just a brief introduction of what we have seen even yesterday to correlation and causation. Let's just, yeah, we saw this from spurious correlations yesterday. Number of movies that Nicolas Cage appeared in, and number of people who drowned by falling in the pool. It correlates very well. These two variables correlate very well with each other, but doesn't mean that uh, the number of films that Nicolas Cage would do would depend upon the number of people falling into the pool. So then, why does so what does causation imply? Actually, what does causation imply? So we also saw this terminology, potential outcomes. So potential outcomes is basically uh, whether when you have been given the treatment, what is the outcome, or if you are not given the treatment, what is the outcome. So in case you have been given the treatment, so understanding the outcome in of no treatment is called counterfactual. So we saw what is counterfactual and what is factual. Factual is the actual outcome, okay, and counterfactual is uh, in the absence of treatment. But think about it, how can you measure that? If you have given medicine to a person, and we are asking a question like, what would have happened if I wouldn't have given the medicine to this person? Like, that's difficult, right? So that's the counterfactual. So potential outcome is inferring the effect of treatment or policy on some outcome. And okay, these are all introduction. Yeah, motivation to causality. We'll skip these through. And then we talked about the average treatment effect. So the individual treatment effect is given by yi1. So one is whether the treatment has been given or not. So potential outcome under treatment. And yi0 is potential outcome under no treatment. And yt is the population level potential outcome. So the individual treatment effect is, you give the treatment and you don't give the treatment, and then subtract the some metric from the treated minus no treated, and you need not sample 50/50. So just take a weighted mean of yi1 and yi0. That will give you the average individual treatment effect. Yeah, which is also associated with the average treatment effect. So you find out the expectation of y1 minus expectation of y0. Okay, so this was the average treatment effect, and then we discussed about the randomized control trials. So how to ensure that the potential outcome is independent of the treatment. So for that, what we do is known as the randomized control trial. You basically randomly sample from the entire population and give so divide it into two groups. To one group, you will give the treatment and don't give the treatment to the other group. So that is randomized control trial. Okay. And in observational studies, this is something which is very useful. If you are like for our field, people who even who are doing model using models, but basically extending the scope of your observational analysis, you can try to understand causality from your data. Ethical reasons won't come for our case because we are not using any humans for our experiments. However, we might face this factor of infeasibility, that is can't randomize countries into communist or capitalist systems to measure effect on GDP. I mean, you cannot, like, it would depend upon some or the other factor. So you cannot isolate the potential outcome from the treatment. And then there is another feature of impossibility. So you can't change a living person's DNA at birth for measuring the effect on breast cancer. And how do we measure the causal effects in observational studies? So you adjust or control for confounders. So you control for the right variables w, and if w is a sufficient adjustment set, so you basically find out the expected yt conditional to w equal to small w. Okay, so yeah, that's it about this motivation for causality. Now we will see this chapter 2, okay, which is on potential outcomes. So what are potential outcomes? What is the fundamental problem of causal inference? Getting around the fundamental problem of causal inference and complete example with estimation. So we'll see what are the potential outcomes. So we have already discussed that these are the possible or plausible outcomes um, that might be the result of taking the pill or not, or treatment or not taking the treatment. For our case, it can be the treatment can be an El Nino and La Nina. So those can be the forcings or treatments in our case. And okay, so these are all similar slides. Anyways, so this is about potential outcome. Now, the fundamental problem of causal inference is to find out the causal effect. So you want to estimate the what would happen if you, or what is the efficacy of your treatment, whether you should give the treatment or not. To decide that, you should know what is the causal effect of that treatment. The problem is that if you are not giving the treatment, okay, you can only measure y0, right? Here counterfactual is y equal to 1, and this the factual is uh, or t equal to 1. The factual thing, or the actual, in reality, what you did was t equal to 0. And if you give the treatment, then your counterfactual is t equal to 0. Like, it's not possible to measure the counterfactual just like that. And then you also then would have to do the missing data interpretation. So for example, you did not give the treatment, right? So y is 0, you don't have y1. Okay, we have y as at 0. So when you are giving the treatment, you can measure that number, or you can measure the state of that person or that system. But for example, if you give the treatment, you cannot measure what would happen if you did not give the treatment. So y1 minus y0 will always be, you can see it's difficult to find out. And this was the fundamental problem of causal inference. How would you get around this problem? So the way to get around this problem is by average treatment effect. So you would basically compute the expected value of y1 minus y0. Okay, and you would take the expectation of y1 and subtract expectation of y0 from that. So yeah, so that eventually becomes expected value of y given treatment equal to 1 minus expected value of y given treatment equal to, or condition to treatment equal to 0. So what is the expected value of y given the treatment is 1? Okay, so let's say 1 corresponds to the person living and 0 corresponds to the person dying. And if t equal to 1, so for t equal to 1 means for the cases where you have given the treatment. So your average treatment effect here will be 1 plus 0 plus 1 divided by total numbers, right? So 2 by 3. And in this case, when you have not given the treatment, you have 0 plus 1 plus 1 and divided by 3. So this becomes 1 by 3. So the average treatment effect then becomes 2 by 3 minus 1 by 3, which is 1 by 3. So that is the way you would avoid the fundamental problem in causal inference. And we have already seen that association is not causation, and we have discussed the example of sleeping with the shoes on and getting up with a headache. Okay, so the common cause might be drinking the night before. And what is confounding? Confounder is like your, so this is the confounding relationship. For example, the red one. Okay, and so the, okay, so sleeping with shoes is uncomfortable. And so you can see that these are the two groups that we have for the t equal to 1 and t equal to 0. So t equal to 1 is whether the person is given the treatment. The treatment can be anything, that person is wearing shoes and went to sleep without shoes on. So that is, let's say, t equal to 0. So these two groups are not comparable, right? I mean, you cannot just compare these two because and associate it with the shoes, because this group contains people who are all drunk, and this group mostly contains people who are sober. So this is something what, like your how your comparable groups would look like. So when to sleep with shoes on, t equal to 1, let's say that's the treatment. And when to sleep with shoes on, which is without shoes on, which is t equal to 0. Now if you compute the expected value of, so y1, so 1 here is the person went with shoes on, y at t equal to 0 is the person went without shoes to sleep. So now if you will compute, the chances are that your like causal effect won't come into picture, or you would quantify that there is no causal relationship of getting up with a headache and wearing the shoes on. So what assumptions would make the average treatment effect equal to the associational difference? So one is ignorability. So your outcome, your potential outcome given the treatment 1 or given the treatment 0 should be independent of the treatment. So treatment should not decide, like it should, the basically the assigning the treatment or should not be dependent upon the treatment itself. For example, if a person has a headache, only then you will give medicine to that person, right? You won't give medicine to a person who doesn't have a headache. So in that case, we won't follow this ignorability assumption. But for causal inference, this is an assumption that you have to make, that there is you have to make this assumption of ignorability. So yeah, next we would see, okay, yeah, we have seen this. Then we have this assumption of exchangeability. So you have two groups, group A and group B. So you give treatment equal to 1 to group A and treatment equal to 2 to group B. So the expected value of y conditioned on treat t equal to 1 is y1, and expected value of y given treatment equal to 0 is y0. So exchangeability assumption says that you should be able to exchange these groups. So you can see that now if you change the position of the groups, okay, so rather than having group A receiving the treatment 1, now you have group B receiving the treatment 1. So your expected value should remain the same. Okay, you can see this. So that is the exchangeability assumption. So your causal inference should not depend on the sample that you take out from the population. Then we have another assumption. It's called identifiability. Identifiability. So the causal quantities that we have are expected value of y1 and expectation of y0, and we call these as the statistical quantities. Expected value of y such that t equal to 1 and expectation of y such that t equal to 0. So a causal quantity is identifiable if we can compute from it a purely statistical quantity. So expected value of yt is like it's identifiable if only if we can compute expectation of y given t. T here is our treatment. And now we have the concept of randomized control trial, RCT. Okay, so you randomize your samples and then give the treatment. So a randomized with a randomized control trial. Okay, so you should have something like this, like equal distribution of the different samples or the different individuals. And okay, so what important property does an randomized control trial give us? So it gives us conditional exchangeability, and it okay. So apart from exchangeability, yeah, this is all on exchangeability. Okay. Also, the conditional ignorability. So we saw what is ignorability. Y0, Y1 are independent of the treatment. So unconfoundedness is an untestable assumption. So we assume in causal inference that we are not having any confounders, or what we are calling as unconfoundedness. So with in unconfoundedness, so we have the first thing that we have is positivity. So for all values of covariates x present in the population of interest, so that is you have the covariate or the different variables as x. So the probability of treatment equal to 1, given that you know that particular variable, so that should lie between 0 and 1. And okay, so that is about positivity. Okay. A lot of repetition here. Yeah, so let us move to the next part, which is graphical models. We also saw this graphical models on the causal course yesterday. So the basic graph terminology. So whether this is a graph, no, this is also not a graph. Okay, then this is a graph, right? We have nodes, we have edges, right? We can call them nodes or vertices A, B, C, and D, and they are connected through these lines or the edges. They are representing the associations. The edges are representing the associations in the graph. Then we can have an undirected graph and a directed graph. So in a directed graph, we can say who is the parent and who is the child. So A is the parent, B is the child here. And A and D are not adjacent to each other, whereas A and B are adjacent to each other. So any two nodes who are connected through an edge, they are adjacent to each other. So this is known as the path. A path is basically a continuous connection. So the edges should be connected to each other, and if you can reach from a particular node to another node, so that forms a path in a graph. This is another path. And then you have so this is not a directed path, but this is a directed path, because you can see that along the arrows, they are going in the direction of the path, that is A to C and C to D. You can also call them as causal parent as ancestor and causal child as a descendant. Okay, and then we have this cycle, the concept of cycle in a graph. So you can see that if you are getting this kind of closed loops, B, C, D, and then again B, C, D. So this forms a cycle. Now we have this concept of directed acyclic graph. So directed acyclic graph is basically a graph which in which you are, if you start from one node, you should not reach that node again. So that is a directed acyclic graph. And so now we'll talk about the Bayesian networks and causal graphs. So okay, you can compute the joint probability distribution of x1, x2, dot 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 up to xn. So which will basically be probability of x1 and multiplied with probability of xi given xi minus 1 up to x1. So you can model the joint probability distribution. So which is which looks something like this. Okay, so you have x1, x2, x3. So what will be the value of probability of x4 given x1, x2, x3? So these are all the possible outcomes of x1, x2, x3, assuming that they can only take binary values. Okay, and all these numbers, then they form the joint probability distribution of x4 conditioned on x1, x2, x3. And these will be a total of 2 raised to power n minus 1 parameters. Okay, so then we have an assumption known as the local Markov assumption, which states that given its parents in the DAG, a node X is independent of all its descendants. So yesterday we have seen that if we have, let's say, this path x1 to x3 to x4, which is for example that a person, he knows, he has causal knowledge, and here we had, okay, so this can be something. For example, he knows DAGs, and here is this variable is, let's say that the causal inference is good. So whether the person, if you know x3, then x1 and x4 are independent. Okay, so then like there is no relationship between x1 and x4. Like if you know x3, then you can directly reach x4. You don't need x1. But if you don't know x3, then x4 actually depends on x1. So given its parents in the DAG, node X is independent of all its non-descendants. Okay. So then we have the Bayesian network factorization. Okay. So you can go back and read what are Bayesian networks and what are the different types of networks. I'll not go into that detail. So then we have an assumption known as minimality assumption, which is given its parents in the DAG, a node X is independent of all its non-descendants. Okay, so you have the parent. So now X basically becomes independent of all its non-descendants. So non-descendants are basically the nodes which would otherwise be the parents of X, right? So which are non-descendants, and adjacent nodes in the DAG are dependent. So these are the adjacent nodes in the DAG. DAG is directed a cyclic graph. They are dependent. Okay, so what is a cause? A variable X is said to be a cause of a variable Y if Y can change in response to changes in X. And in a directed graph, every parent is a direct cause of its children. So we have two assumptions to give us flow of association and causation. One is the Markov assumption, and another is causal edge assumption. So what are the building blocks of the graphs? We have nodes. So let's say these are the two nodes. Or okay, so this is also another building block of the graph. You can have a chain, you can have a fork, okay, and we can have this type of structure. They're calling it immorality. This is also known as something else. Yeah. Okay, so what assumption tells us that x1 and x2 are associated given the following graph? So the assumption is dependence, and okay, so much of yeah, it's also called as a collider. So in a collider, the difference between a fork and a chain and a collider was that only in a collider, if you know about x2, then x1 and x2, x3 are dependent on each other. They are not independent. So independence in a causal graph is also known as d-separation. We'll see d-separation later. So okay, so if we condition on the collider, then this path gets blocked. So then these two guys are dependent on each other. Okay. Yeah, so then they have an example, the flow of, yeah, we have seen these things yesterday. And now I will Okay. So I will show you this paper inferring causation from time series, like how this is used in our field. And these are a set of, so there is a library that you should know about. It's called Tigramite. Okay. So Tigramite is a causal time series analysis Python package, allows to efficiently estimate causal graphs from high dimensional time series datasets. So you can do causal discovery and to use these graphs for robust forecasting and estimation and the prediction of direct, total, and mediated effects. So the maintainer of this library is Jakub Runge. You can go to his page and see his Tigramite library. So he has been publishing these. So you can see these papers. So detecting and quantifying causal associations in large nonlinear time series datasets. This is in Science Advances, and he has this Nature Communications paper identifying causal gateways. So the one that we have opened here. No, this is not that one. This is another one. This is 2015. I think this is 2019. Yeah. So he has a series of Nature Communications and Science Advances papers. So the method that he has developed is called Pcmci, and in this paper, which is titled as inferring identifying causal gateways and mediators in complex spatiotemporal systems, they are proposing that now you have the data set over the entire globe, entire earth. You basically at every grid point you have a time series, right? Do a dimension reduction, which would yield regional components of the from your data. So just make these different time series x, w2, w1, y, z2, z1. Now from these dimension reduced uh, variables, what you can do is causal reconstruction, including time lags. So you can basically construct this kind of a causal graph, and you can do causal interaction quantification. So you can find out what what does, for example, this mediator, what would it do, and this would in turn give you the importance of nodes or via aggregated node measures. So you can basically derive physical relationships in your data using this technique. Okay, so this is the dimension reduction of an atmospheric dataset. So map of 60 Varimax components enumerated from 0 to 59. So he's first doing this, and then results for the teleconnection between ENSO and Indian Ocean within the causal network of pressure components. Now you can also quantify the causal effects. So then there are causal gateways and mediators. Can see this paper in detail, and then they talk about this discussion. Okay, so for the method which is developed by Yakub, there is this technique. It's called PCMCI. PCMCI stands for Peters and Clark's Momentary Conditional Independence. Okay. Now they have also introduced PCMCI plus, PCMCI plus plus. Okay. So I will explain maybe PCMCI and then close this class. Uh, so that is, yeah, just give me a moment. I will. Okay, so one of these papers has got the explanation. Yeah, this one. Okay, so in PCMCI algorithm, for example, you assume that you have these time series, okay? A, B, C, D, E, F, G, and you want to identify the, you want to find, establish the causal discovery graph between all these set of time series. What you would do typically in a traditional sense is you would compute correlation between pairs of the different time series, and we are assuming we are keeping an assumption that at time tau equal to 0, okay, so each letter in P represents a univariate time series, which in our case must be given in the form of detrended anomalies. So the PC algorithm first calculates the plane correlation between the first element at lag 0 and each of the remaining elements at in P at certain lag tau equal to 1, 2, or whatever is the maximum lag that you have defined. Now, what you would do is that, for example, A at tau equal to 0, or which is the actual time series, you would find out its correlation with the other series at different time lags. For example, for all the series, you were able to zero in to these four: C at tau equal to -1, D at tau equal to -2, E at tau equal to -1, and G at tau equal to -1. So these are the four series which have four time series which have got good correlation, or which have got statistically significant correlation with A at tau equal to 0. All the others have non-significant correlation with A at tau equal to 0. So this is our first step. So PCMCI can be broken into PC plus MCI. So we are talking about the PC step. Now what you will do is, now you would want to find out the whether actually C and D, let's say for example X and Y in these, so these are all causal parents of A. Now you would want to find out whether they are actually the causal parents, or something else is driving them and then they are leading to a change in A, or that is driving them to be a parent. So we basically are trying to find out the confounders. So what we will do is we will say, okay, let's try to find out the correlation of X and Y, between X and Y, conditioned on Z. Okay. So what that means is, for example, the correlation between A at tau equal to 0. So A at tau equal to 0 and C at tau equal to -1. So C is a parent of A. So we are trying to find out these two, the correlation of partial correlation of these two, but conditioned on D at tau equal to -2. So what we will do is we will make an equation, for example y equal to mx plus c, where your independent variable is D at tau equal to -2 and dependent variable is A at tau equal to 0, and from that equation we will find out the residual. Okay, so we will basically take out the effect of D at tau equal to -2 from A at tau equal to 0, and we will take out the effect of D equal at tau equal to -2 from C at tau equal to -1. Now once the effect of D at tau equal to -2 has been taken out from A at tau equal to -1 and C at tau equal to A at tau equal to 0 and C at tau equal to -1, if they are still having a good correlation, then you can say that C is actually a causal parent of A and D doesn't have any role to play. Now, it might happen that when you are trying to take the effect of confounding effect of C at tau equal to -1 from D at tau equal to -2 and A at tau equal to 0, and then find out the correlation between the residuals of A and D, you might then get this. you might then get that this d at tau equal to -2 is not a causal parent of a at tau equal to 0. Okay, so you will do this for all the pairs and like all the permutation combination, taking the one confounder as a you will take condition to one confounder, then you will condition on two confounders. So you will keep doing this as long as it is possible and keep removing the causal parents. So in the end we get that c at tau equal to -1 and e at tau equal to -1 are the only causal parents of a at tau equal to 0. And then you will do this, you will find out in this similar manner, you will find out the causal parents of c at tau equal to 0, e at tau equal to 0. Now this was our PC step. Okay, so this concludes our P step. Now we will do MCI. Okay, momentary conditional independence. In MCI, what we will do is we will check for the parents of the parents. Okay, so for example, for a at tau equal to -0, we will, let's see its relation with c at tau equal to -1. Now c at tau equal to 0, its parent is one of its parent is a at tau equal to -1, right? So this is, yeah, so basically for c at tau equal to 0, the parent is a at tau equal to -1. So for c at tau equal to -1, the parent will be a at tau equal to -2 and d at tau equal to -2. So we are checking for the parents of we are taking out the effect of parents of c at tau equal to -1 from itself, and we are taking out the effect of these two guys from a at tau equal to 0. And still, if the correlation is significant, we will see that okay, c at tau equal to -1 is actually a causal parent. Now these we are talking in terms of checking the relationship with correlation. You can also do that with different other non-linear metrics like mutual information. You can do with Gaussian process regression, because an argument can be made that correlation is also linear. So after you do all these calculations, you will get for each variable who are their causal parents, and then you can construct the causal discovery graph. So this is about PCMCI, and I would suggest you to go through these papers. It is this library is available openly for anybody to use, and will greatly supplement your observational analysis, or even if you are doing analysis from model outputs. So you can construct the causal discovery graph using PCMCI. So with that, I would conclude today's class.